Thanks for tuning in. My name's Dillon Amaya. I'm a postdoc at the University of Colorado Boulder, and today we're going to talk about the influence of climate change on marine heat waves. This work was done in collaboration with my co-authors, Mike Alexander, Antonietta Capitondi, Claire Desser, my postdoc advisor, Chris Karnauskas, Art Miller, and Nate Mantua. So thinking about marine heat waves sort of as a phenomenon, I find them really interesting because they span these really large spatial and time scales. There's just a wide range of different kinds of marine heat waves out there and the different dynamics that are most relevant for driving them. But today we're mostly going to focus on marine heat waves that exist on sort of these really large and long time and space scales, the ones that take up entire Pacific Ocean basins and can last for months and seasons and potentially even years. And as a result, they can be strongly influenced by long-term climate change. And people have thought about the influence of climate change on marine heat waves in the past, but mostly through a statistical lens. Looking at climate model projections, people have shown that, or researchers have shown that in the future, marine heat wave days are more likely under global warming due to a shift primarily in the mean SST. The idea being that if you shift the distribution of SSTs, or sea surface temperatures, towards warmer values, then of course you're going to have more, you're going to be more likely to experience the tails, and those tails will be stronger than they were relative to present day. But really, my question here is just sort of to take the next step. Can we think about the dynamics of what drive large-scale marine heat waves, let's say in a mixed layer temperature budget perspective, and can we think about how climate change influences the specific processes that lead to a marine heat wave? And ultimately manifest themselves as those statistical shifts that we see in the distribution of the SSTs. So that's really the question we're after today. What dynamics drive the projected increase in marine heat wave frequency and intensity in the future? So to think about this, we're going to think about the influence of climate change actually on a specific case. This was a marine heat wave that occurred, or at least was initiated in the summer of 2019, what we're calling this blob 2.0, because it had strong sea surface temperature anomalies in a similar location and in a similar blob-like structure in the Northeast Pacific. And we can think about how climate change led to this, or contributed to this, this marine heat wave through a mixed layer temperature budget approach. And this is a basic mixed layer heat budget. And what we really want to do is simplify this a little bit so we can focus on individual terms explicitly. So the first thing we're going to do is only consider local heat sources and sinks. And we're also going to ignore diffusion. So all we're going to do is lop off ocean advection and large scale diffusion. And we're going to linearize this. We're going to linearize the surface heat flux Q and the mixed layer depth about some mean state and some perturbations, some anomalies, and we can tailor expand to get a nice linearized and simplified mixed layer heat budget with 4 terms that we can think about in detail here. And so the question really is, how does climate change influence the terms on the right-hand side? Because we already know what happens on the left-hand side, right? That's those statistical analyses. We know that T prime, the SST anomalies in the future, the marine heat waves, will be more extreme and their occurrence will be more frequent. But what is it about the terms on the right-hand side that generate those more frequent and more extreme SST anomalies in the future? Let's more specifically think about changes in the mixed layer depth, H here. Well, in the future, we expect H bar to decrease. We expect the mixed layer depths to shoal, and that's because upper ocean stratification should increase in the future as the upper part of the ocean starts to warm, and the deep ocean just isn't warming as quickly, which makes it harder to mix cold water from below the mixed layer, meaning the mixed layer will just continue to thin. And so that has really interesting implications for these first 2 terms. For one thing, term 1 says that in the future, if we have a shallower mixed layer depth and we reduce the denominator here, you're going to get a stronger SST response for the same heat flux anomalies. Term 2 also takes advantage of this relationship and says that if you reduce the denominator here, just by reducing the denominator, even if you didn't change Q bar, you would get a stronger SST response for the same mixed layer depth anomalies in the future, just by virtue of having shoaled the mixed layer by squishing that volume to smaller values. This second term is actually not only, but mostly important in the summer, as we'll show a little bit later. So the question is this already occurring? Has this happened in the historical record? And what does that look like in the future? Well, we can look in the historical period by looking at mixed layer depths averaged in this Northeast Pacific box. That's this purple line here, this purple time series. This is the summertime mixed layer depths averaged from 1980 to 2019 in Godaz ocean reanalysis. You can ignore this green line for now. But basically what this shows is that there's a really strong and significant downward trend here. There's a shoaling trend in the mixed layer depths in this Northeast Pacific box. But interestingly, in 2019, there were really extremely negative mixed layer depth anomalies that, as we showed in a separate paper, were really important for the development of this 2019 event, this 2019 blob 2.0. And if these mixed layer depth anomalies were riding this long-term trend, well, there was much more likely that they were to happen. So if this mixed layer depth trend is real, if we can show that it's real in other observational products, then it's possible that the mixed layer depth anomalies that were essential for this blob 2.0 were exacerbated by the trend, and the overall blob 2.0 was intensified by climate change, if we can show that the trend was also due to climate change. So that's what we're after here. Did climate change influence the summer 2019 Northeast Pacific marine heat wave? Really, did climate change contribute to that observed mixed layer depth trend? And then a second question is, how representative were the 2019 mixed layer depth conditions of the future? Was this a preview of what is to come, given the long-term shift of the mean towards shallower and shallower values? And then finally, can we generalize this? Can we think about how the shoaled mixed layer will influence the magnitude and frequency of marine heat waves in general in the future? So to do this, we need to first convince ourselves that the mixed layer depth trend that we just showed is real. To do that, we're going to look across different observational reanalyses, ocean reanalyses. Obviously, we're also going to compare to Argo profile where the records overlap. But to isolate the effect of climate change on the historical trends, we're going to look at the ensemble means of the CSM large ensemble, which has 40 members, and then also 13 models from CMIP5. And these are the 13 models that outputted the ocean variables that we needed to calculate mixed layer depth. Speaking of which, we calculated mixed layer depth explicitly for all of the products so that it was consistent across them. We calculated it as a potential density jump, where the potential density was calculated from TS profiles. And this was the potential density jump we used, although I'll just say that the results are very consistent when you use a different potential density jump. So it's not sensitive to that at all. So let's look at the mixed layer depth trends and observations. This is that same mixed layer depth time series that we saw in GODAS earlier for summertime mixed layer depths in the Northeast Pacific. And this is the time series. These are the time series from all the other ocean reanalysis products and Argo here in blue. And basically what you can see is that prior to the Argo era, which is about 2000, you can see this divergence in the observational reanalyses here. You can see that there are these haves and the have-nots, those that have a trend and those that really don't have a strong trend. Although I will note that during the Argo era, the interannual variability is really good across they agree across the ocean reanalyses. And Argo also shows a significant shoaling trend during the Argo era. And this is consistent in space. You can see that GODAS and ORAS5 have long-term trends that look very similar to each other in the mixed layer depth, where blues are shoaling and reds are deepening of the mixed layer. You can see these two hotspots in the Bering Strait area and off the west coast of California, whereas ORAS5 and SOTA3, they have hints of sort of these two hotspots, but just not nearly as coherent in large scale as they are in the other two ocean reanalyses. So again, these sort of haves and have-nots. We could average together sort of the haves and the have-nots into two sort of mini observational ensembles and compare them to mixed layer depth anomalies during the summer of 2019, which are shown here in shading. And really the spatial consistency, to the degree that we trust the observational trends here, the consistency between the trends and the anomalies during JJ 2019 really suggests that the trend exacerbated the likelihood or increased the likelihood of these mixed layer depth anomalies and exacerbated the intensity of the 2019 marine heat wave just by virtue of making those mixed layer depth anomalies more likely, because the mixed layer depth anomalies were really important to the overall intensification of the sea surface temperatures, which are contoured here in red. These are the sea surface temperature anomalies during that event. So the question is, are these mixed layer depth trends in the historical record, are they due to climate change, if that's the case, or are they due to internal variability? Well, we can look at model trends. This is the ensemble mean trend in CSM1 and CMIP5 across those 13 models during the same historical period. And for one thing, you can see that there's some model uncertainty as to the strength and the general spatial pattern of the forced trend in the historical period. But there are some general consistencies across between the observations and CMIP5, sort of hints of those two hotspots. But looking forward, you can see that there's actually a much stronger comparison, a much more consistent comparison between the observations and the force trend looking out towards 2100 in both CSM1 and CMIP5. They both have sort of this horseshoe type pattern these two hotspots are more apparent in the future projections. And so this may suggest that the models, there's some uncertainty in the strength of the historical trend, and the models may be underestimating the strength of the historical trend, the forced historical trend in the observations. But given the observational uncertainty and given the model uncertainty, we can't conclude that the trend is due to anthropogenic forcing. It seems to be mostly due to internal variability, but I will just note that there's this uncertainty in the strength of the representation of the forced trend in some of these models as well. Right, and the observations just share some spatial characteristics, but it is pretty clear that these trends will be exacerbated as you go forward into the future and only become more intensified, even if they were due to internal variability. So now we can think about this more generally. Let's think about mixed layer depths in the Northeast Pacific in that same box. Again, in observations, which are in red and orange here, those haves and have-nots. We also can compare it to the long-term projected trends in CSM1 and CMIP5. And you can see that by the end of the century, both CSM1 and CMIP5 project a very consistent about 4 meters shoaling of the mean mixed layer depth in the summer. That's something like a 20 to 30% decrease in the climatological mean summertime mixed layer depth in this region, which is pretty substantial, although there is a lot of internal variability here, a lot of noise in the system. But what does that mean for the manifestation or the likelihood of mixed layer depth anomalies, like the extreme mixed layer depth anomalies that we saw in 2019? Well, this PDF distribution shows the distribution of mixed layer depth anomalies in a present period in CSM1. And you can see that the observed 2019 anomalies, which were really important for the blob 2.0, were way on the edge of the tail. They were very rare events. But if you take into account the future shoaling, the future shift of the mean mixed layer depths towards shallower values, you can see that in the future, these sorts of anomalies are going to be much more common, right? This is that same argument that people make about marine heat waves and SSTs, but this time applying it to mixed layer depths here, that by shifting the distribution towards shallower values, you obviously are going to increase the likelihood of extremes. And in this case, the 2019 mixed layer depth anomalies increased to something like the 7.5 to 10.5 percentiles based on this model. So they'll become much more common in the future. And then finally, let's connect this back and think about how these changes in the mixed layer depth that we're seeing here influence marine heat waves in the future in general. And so the way we're going to do that is look at terms 1 and 2 of this linearized simple mixed layer heat budget and see how changes in H bar and changes in Q bar in future climate model projections interact with Q prime and H prime to generate SST anomalies, basically. So in CSM1, this is the JJA mean mixed layer depth in red here. So you can see that shoaling again. And then blue here, we see the JJA mean net surface heat flux in CSM1. So the net surface heat flux is increasing out toward 2100, but the mixed layer depth is again decreasing out towards 2100. So what does that mean for the kinds of temperature anomalies that term 1 and term 2 would produce if you fixed, say, Q prime and H prime? Let's say that we wanted to look at the temperature response. We wanted to look at the left-hand side, given some Q prime and H prime that were exactly the same as what we observed in JJA 2019. So if we just fixed Q prime and H prime and we pushed it forward, and all we're doing is changing H bar and Q bar, this is what we would get. This is the T prime. This is the SST anomaly that you would get if you kept those two things fixed. Term 1 is much smaller than term 2 here. So let's talk about term 2. Term 2, because you increase the denominator and you decrease the denominator squared, you really get a strong impact on the mixed layer temperature budget. So basically what this is saying is that the same H prime and Q primes in 2019, but acting on a shallower mean mixed layer depth in the future, will generate a 4.5 degrees more warming than present day for the same Q prime and H prime. A couple caveats here. Term 3 is really small, so we're not plotting it, but term 4 may balance some of this. So this seems like a really scary anomaly, something like 10 degrees Celsius, but it's going to be balanced by some changes in entrainment as well. And we're not showing that because entrainment is really terms 4 through 7 here. It's really scary, and there's a lot more work that needs to be done to quantify this more directly. But this is telling that changes in mixed layer depth and the mean net surface heat flux could lead to drastic changes in the representation of these in the heat budget. So just going to leave you with some take-home points here. I'm really excited to talk with people about this in the next couple weeks. Here are some relevant papers for you if you're interested in this work. This work was published in BAMS or will be published in the near future. So thank you. Bye.